Hello, everyone. Welcome to another binary episode of the Day Zero podcast. I'm Spectre. With me is Z. Today we have a bit of a light episode, but we do have a KASLR bypass detailed by a trail of bits. We have an interesting out-of-bounds write chain in FortiGate, and some topics from Microsoft's Phone Research Lab on Mojo exploitation. So we'll start out with a post by Trail of Bits. So this is detailing a KASLR bypass in privilegeless containers. So they talk about Docker primarily here as the main driver, but I'll let Z get into the details.
Yeah, and the post starts off with like this JWT issue and this JSON object signing and encoding thing. That's unrelated to what the attack we're going to talk about. It's one of those weird times where they're kind of doing two topics here at once. They kind of draw things together at the end in terms of do you need audits. But anyway, so the other thing I will say about this bug is it is from 2020. I'm not exactly sure why we're just getting this kind of information about it from Trail of Bits now. If they maybe published about before and now they're bringing it back up for this post or whatever.
Well, they do state that it didn't get a CVE assigned, so it might have been that they were waiting some time because of the fact that it wasn't posted as a security advisory. So
Maybe
that's my assumption.
It's still several years.
It is
Like
a while,
it's still quite a while, and like it's there. It could be explained, but yeah, because their disclosure timeline for this is just like we reported the vulnerability in June of 2020, and by December they still hadn't heard anything back from Docker, and then we're in 2024 and they disclose it. It's like there's nothing between there. Anyway, so a little bit weird on that front. Nonetheless, I think it's a kind of interesting bug. Not really a memory corruption issue, but definitely has an impact into memory corruption because this is a kernel ASLR bypass. Generally, your bypass on that is going to be by leaking a pointer so that you can basically do all your relative calculations from there, because KASLR and ASLR in general only tends to work by changing like a large offset and not like the relative addresses of things. So the distance between two things will still remain the same.
very low granularity generally.
Yeah, I mean, you can get into fine-grained ASLR, but we haven't really seen that hit any sort of take-up, especially not in the kernel. To kind of understand this bug, though, you need to understand a few things that are a little bit kernel-specific. And that comes down to, one, like kernel ASLR does kind of exist in a different realm than standard ASLR, just because the kernel is this always running process. You're not like going to get a like not going to have ASLR reseated on every boot. Well, you'll have it on every boot, but like the kernel doesn't boot as off as like a user lab program, little things like that. And there are these interactions going on from user space, kernel space. So oftentimes there can be places where kernel pointers will leak. One of the places where kernel pointers can intentionally, in a sense, be leaked is within the pseudo file systems that exist. Things like sysfs and procfs. If you've ever seen like slash proc is like a in the file system, or slash sys, those are not real files that exist, but they're kind of when you read or write those files, the whole Linux idea of everything is a file extends there, where it's like those files are actually being passed into other programs and their pseudo file systems. And so
They're kind of like system calls, but implemented in the file system.
Yeah, and giving text back specifically, whereas system calls are going to give you more structured data back. They're giving you, whereas the pseudo file systems are kind of meant to be a bit more human usable. Like you might go into your shell and like cat a file under procfs in order to find out something about like the process, so you can find out things like the memory mappings or the sections in that, which is kind of the case that they end up calling out for this bug, where they go and desist the modules and then sections under there, and you can use that to actually get pointers, or presumably get the pointers of where something might be. But it's basically the pseudo file system interface that exists. It's a little bit weird, not something you see in many other applications, because the kernel is kind of special, and Linux specifically has this whole everything is a file concept going on, or paradigm going on with it. The other thing is kind of associated with that, or are sys controls or kernel parameters that can be modified at runtime. and you can modify them through the sysfs or the sys pseudo file system. So that's another way the pseudo file system's getting used. Like you can write a value to these kernel parameters through sysfs to change their runtime values. So again, those couple things are just kind of weird Linuxy things for how you're interacting with these systems, but the vulnerability doesn't really depend on understanding too many details about them. Just the fact like that's how things are being interacted with. And then the last thing is capabilities inside of Linux kernels are kind of just like privileges where you can be root but not necessarily have all of the capabilities associated with it. So you might have the root user ID, like user ID 0, but only have like a specific capability, or you can give something a specific capability. And they're just capabilities reflect different privileges. Like there's net admin sort of capability. The one that matters here is something called KASLR. But there's a ton of them that just basically give different privileges. That way you can give something without giving the keys to the kingdom in a sense.
Yeah, I mean, I was just gonna say this kind of setup is important to understand for things like Docker and virtualization, where you want to be able to give a container fake root to be able to do the things it needs to do, but you don't want to give it full capability over the whole system. So that separation of privileges is important for that.
Yeah, and then you can kind of also get into namespaces, but I don't think that really plays into it here because fundamentally the issue, now I'm finally going to get to it, is as I was talking about how in the sysfs you can end up having pointers written out there and getting displayed. Usually you've also got this control, the kernel parameter for k pointer restrict, which can have 3 values. If it's set to 2, then pointer addresses in sysfs are basically just always hidden. It's not going to show the pointer address for any reason. If it's set to 0, then it means they're always showing. And like you have no security. Any user that has access to this. That is also worth noting. sysfs kind of benefits from the fact that files in there are root owned and therefore only root can access them. So there's a little bit of the user level access control going on with that too. Anyway, so value of 0 is always shown. Value of 1 means that the pointers will be shown, but only if capsyslog, or if they have the syslog capability. So basically you've got those 3 cases, and the problem seems to be that some of the sysfs interfaces would do this check incorrectly. Specifically some that came from Docker, or could be used under Docker at least. When they did this check on the pointer, and let me pull up the code here, what would end up happening is it would just check if the k pointer restrict value was less than 2. So that was the 2 options for that, or 2 was that they're always hidden. So basically just checks, are these always hidden? No. Okay, let's show the address. So it's just a bad check. Like it is a very simple issue to understand there. It's just how this
just ignores the
kicked
capability entirely.
Yeah, basically just ignores that entirely. And in a lot of cases, like this was still kind of sufficient because this sysfs is kind of limited to, or at least this part is limited to being accessed by root. Like these are root owned files. Everybody else is denied read, write, execute access on it. Just root gets to read it. Oftentimes, if you are root, you have all the privileges. Like that is kind of the common setup, but things like Docker change that. In those cases, you do have unprivileged root, where you're root, but you're inside of this weird little namespace. And so inside of Docker, you could go ahead, be root, read this file, and get all the pointers, even though you shouldn't be able to read the pointers, and basically use that to break the kernel's ASLR. So yeah, fundamentally,
which is notable because when you're breaking the kernel, like you doing that from a container context to escape the container is one of the prime strategies of container escapes. So it's definitely a fair like impact and threat model there.
Yeah, like this, because this would enable, if you were inside of a Docker container, you get root. Basically, at that point, like you just don't have to do any extra work to break kernel ASLR. You still need to break the kernel, like you'd still need the kernel bug, or some other container escape. There's a ton of ways to do that besides just attacking the kernel. But if you were to attack the kernel, this just gives you like a trivial address leak because you can just
Yeah.
read. And this existed in multiple places. They said they reported more than one case of this to Docker and to the Linux security team. Uh,
Which definitely
and
makes sense because given how the code is written, like it's not really centralized. It's up to the individual drivers to ensure that the permissions are correct, like the caller has the right permissions. So I could definitely see a lot of variance of that for sure.
Yeah, so fundamentally, the issue is really simple. Like, it is just they're not doing the check correctly. They have a ternary where they have three possible values, but they only check if it's one value and assume everything else is okay. Which, again, I kind of get if you're thinking about it from just the whole root access thing, but yeah, just ignoring the capability aspect entirely. Uh,
Yeah. Sorry, I do want to make a quick correction to what you said. So with the K pointer restrict, if it's 0, it's not really just you can read it. If it's 0, the address is hashed before it's printed out. So it'll hash the pointer. So it's not really a useful pointer for doing anything with. So 1 and having that capability is kind of the unique case where you get the actual pointer value. So yeah,
okay, I
K
thought
pointer
only
restrict
with
is a little
two
bit
it was
weird with how it
hashed.
works.
Yeah,
So with
okay.
2, it replaces the pointer with zeros, and in 0 it's hashed, and then in 1 it's either the real pointer or it's zeros if you don't have the capability. It's kind of weird with how they do
Okay,
it, but
yeah.
yeah.
Yeah, okay. That's just my misunderstanding. Because I knew they did some implementation right actually at the printf level too on that. And that's where I remember seeing the hashing stuff.
Yeah,
Okay,
it's
yeah.
funny
Just
because like I know this, but like I always forget it, and I always have to look up the K pointer restrict manual page to actually like remember what the values mean. It's not super intuitive, but yeah.
all right, fair enough. That's my bad there. Either way, like the bug itself just comes down to that check being wrong. There's just all this
Yeah, for sure.
complexity around how this area works that probably is going to be too helpful when it comes to other systems, but checking it seems like we've found or not we found, but like we found a number of write-ups or we've talked about a number of write-ups where these sort of ternary values where something has three possibilities just seems to lead to bugs because people forget it's got three values instead of two or like treat it kind of incorrectly when it's not specifically set up as like an enumerator or something where they can just enumerate the possible values.
Yeah, yeah, it's an unfortunate design pattern. So, uh,
Yeah, something to consider when you're looking at code, I guess.
all right, so we'll get into our next topic here. So this was an exploit for an out-of-bounds write in FortiGate SSL VPN that was posted by Asset Note, and it's a bit of a fun exploit because their out-of-bounds write is pretty restrictive. Now, I will say up front, I'm going to skip some of the background they go into on this post because they do go into some detail on how they extracted the binaries and patch diffed, and they go into a lot of detail on how they got a debugging environment set up for the exploit. It probably interesting to you if you're looking at Fortinet specifically, but otherwise, yeah, I'm gonna skip over it for covering it. But when they did patch diff, they noticed two changes in the functionality for processing HTTP requests. The first was a check that was added for processing HTTP trailers after a chunked body to ensure that less than 1024 bytes had been read so far. And there was a second check that was added to ensure that the provided chunk length strings were less than 17 bytes. So they were like, okay, that's interesting. Started doing some testing. They were able to trigger a crash eventually by sending a chunked request with a 0 length chunk that had 89 chunk trailers. So sort of an unreasonable request, but that's how it typically goes in these situations. And what they found was that the trailer was read into the stack, and the CRLF value, so hex A 0A 0D, was written to an offset into the buffer. That offset would get incremented and advanced for each trailer, but the offset for the CRLF wasn't properly checked against the buffer size, so you could basically advance that offset beyond the buffer to get an out of bounds write of hex 0A 0D on the stack. But this is a very restrictive primitive. It's only 2 bytes that are being written, and you don't control what the bytes are. You do kind of have control how far out of bounds you're able to write, because it's ultimately derived from the amount of data that's read when processing the chunk. So as I saw it,
Just
there's
before you go on, sorry, I did want to
Yeah.
comment there that the two checks that they seem to have here, the amount of data being read before hitting the chunk trailers, and the chunk trailers, if you're not familiar with chunk encoding, are like when you do your transfer encoding chunk, you can provide headers kind of after everything else has been sent. Those are your trailers. So like when they say 89 trailers, their example crash here, they sent this header named A with a value of X 89 times at the end. So that's a trailer. But I don't know, these checks that they do, like 1024 bytes before getting to a trailer, or the check length of 17, doesn't seem related to what you just mentioned, where, oh, they sent a bunch of trailers. Like, that doesn't like, I don't see where the chunk length comes in. And in fairness, Asset Note called out exactly the same detail.
I was about to
Weirdly,
say Asano called this out too.
yeah, weirdly,
Um,
neither of these seem to violate the new checks as we understood them. So it's a little bit weird on that front, but it is what they manage. So if you're listening along, though, it's fine that you don't see the connection.
yeah, I mean, my assumption is that these are like flimsy checks that they put in because the issue wasn't fully understood or fleshed out, and it just happened to kind of mitigate the payloads that were being used, but it wasn't a very good check. So that's kind of how I read it, but yeah, so they have this ability to write these 2 bytes out of bounds on the stack. So as they saw it, there were 4 potential options that they could use for taking this to privilege escalation. They could do the classic return address overwrite. They could overwrite the saved base pointer to try to hijack some of the locals and the call stack, or they could overwrite saved local values, either just miscellaneous values or heap pointers. Ultimately, what they went with was setting heap pointers because the return address override strategy wasn't very viable because the write was too restricted, right? They tried changing the return address, like the lowest 16 bits, to the hex 0A0D, but that wasn't a valid gadget, so that was very quickly just ruled out. The saved base pointer also wasn't really that useful because the stack didn't seem to be used for very many variables. Most of the variables were optimized to registers, so they got kind of unlucky there. But they were able to find a local heap pointer that would get stored in this in the R13 register, which consisted of an object that had function pointers. So that's what they went with. They basically heap sprayed to try to get a procedure linkage table or PLT address at a correct offset for one of those function pointers, and then they use their out-of-bounds write to do a partial overwrite of that pointer to point into their heap allocation, and then use that to kickstart a ROP chain. So just a nice example of how you can have a really limited primitive that seems kind of hopeless at first, but using some creativity and leveraging the heap and some of the determinism there, indeterminism there, you can still take it to a full exploit. So that's what I liked about this post. Like I said, there was a fair amount of nuance that I am leaving out. For example, like they tried trying to do a system, like a ret to system style attack without having to do a full ROP chain, but there was some problems there because the binsh binary that was there that they would usually execute with system wasn't actually a proper shell. It was sort of a restricted functionality binary, so that's why they had to go with a ROP chain. But yeah, they go into a lot of that detail that's a bit too target specific, so that's why I'm not talking about it here, but it's noteworthy that it's in the post. So
Yeah, the post itself has a lot of the background information, a lot of what they were thinking going into each of these steps, like how they kind of work their way there. Like you, I do appreciate seeing, just taking the pretty limited primitive of a fixed value 2 byte overwrite, or not overwrite, but out of bounds write. I mean, the partial overwrite is a technique that it's been around forever, but don't see it get used super often. At least like
it's
partial
kind of
overwrite
your
on a
path
pointer.
of least resort in a lot of cases, but it's cool when it works out for you when you're able to get it to work.
Yeah, for sure. So I appreciate kind of that aspect of the exploit route here.
Yeah. All right, so that's all we have for exploits this week. We do have a few shout outs and posts that
We
we
have
found
more
interesting.
shout outs than we have actual topics this week,
We have a lot of shout
unfortunately.
outs. Yeah. So the first of which is a post by Microsoft's Vuln Research Lab on making Mojo exploits more difficult. Where this is talking about Mojo, I don't want to go too deep into this because it's something that I haven't really worked on. But for those who aren't familiar with what Mojo is basically the IPC mechanism that Chromium uses to talk to native applications and libraries. And because of that reason, it's been a very attractive target for security researchers for a while, because it's an attack surface that can allow breaking out of the browser sandbox, and where it's native code, like, there's that possibility for memory corruption. One of the things that it has is JavaScript bindings, which they refer to in this post as Mojo.js, which allows JavaScript to access some of the interfaces that Chromium allows. And because this is a pretty big glaring attack surface, Mojo.js is generally disabled for untrusted web content. It's only really allowed on trusted tabs or like special command line options. The problem is, though, if an attacker can compromise the renderer, they can just re-enable Mojo.js by changing the property for that in the render frame. So Microsoft sought out to mitigate this, and they basically added a property to not just the render frame, but also the renderer process. And that property is stored in read-only memory. So the idea there is, you're not, even if you have an arbitrary read-write primitive, you're not going to be able to write into that read-only property and just turn on Mojo.js. So yeah, I mean, it seems like kind of good intentions there. From what I've heard, though, this probably won't be very effective, because an attacker can basically just re-implement what Mojo.js does using a read-write primitive. And once someone writes a framework to do that, it's kind of permanently bypassed. So how effective this mitigation will really be, it doesn't seem like it will be all that effective, really. But it still seems like an interesting step, and it doesn't seem like it'll be costly or anything. So it seems like basically a free way to make trying to hit the IPC a little bit harder. But yeah, it seems to fall into that category of a fair amount of Microsoft's mitigations, where it's like it's effective for a day, not very effective after that.
Well, it's effective for a day, or it does increase the level of work that needs to be done. And like I said, it is relatively free. Like, it's not like this some big performance hit, some big re-architecting of everything. They're preventing a very simple thing that enabled some very powerful access and making you kind of work for it. So, it's still not a bad thing for them to do. It's just, it's not really stopping the exploits, but it will, perhaps prevent end days that have already been written from, maybe using that technique now won't work and need to be updated. Kind of just requiring that constant update, that constant maintenance over things.
That's a fair angle I hadn't really considered, actually. The existing exploit payloads that have been written. Yeah, that's fair. But yeah, we wanted to shout this out because for people who are doing browser research, specifically Chromium, and are interested more on the Mojo side of things, maybe this is worth taking a look at and seeing if there might be some other ways to bypass it. But yeah, where I don't do too much of the Mojo work, we didn't want to go too deep into it. The next shout out that we have was from Ben Hawks, and it's on Robot Stream of Root Shells. So this is about the Artificial Intelligence Cyber Challenge, and mainly about using LLMs or large language models to both find and patch vulnerabilities. As we've kind of seen, I remember we had a few spot the vuln challenges that we tasked like ChatGPT or whatever to try to find issues in. It's not great for that. There is a lot of hallucination on detecting false positive vulnerabilities or just missing vulnerabilities and stuff. It doesn't seem to be quite there yet. But the goal of this competition, the DARPA competition, is to try to address that and be able to make integrating LLMs with security tooling more viable. So this is basically Ben Hawk's opinion post on it. He has some interesting insights on it, which is why I wanted to shout it out. It's not a very technical post. Like, even if you're not super into LLM security research or anything like that, like, it's very digestible. You can get through it.
Yeah, and to be clear, I don't think the AI cyber challenge here is really focused on specifically LLMs. There's Ben Hawks calls out like two possible strategies. I forget exactly what he called it out as, so I can't do a control F for. And one of them are kind of involving LLMs in there, but I think their goal kind of similar with the DARPA Cyber Grand Challenge some years back. Back then, they kind of had this focus where they gave they wanted AIs to be able to discover and patch vulnerability and I think they wanted them to discover, patch, and exploit vulnerabilities and basically toss them onto like a DEF CON. They actually did compete at the DEF CON main CTF game. and kind of going for everything. This one seems to be more just take the AI, find the vulnerabilities, but they don't need to exploit the vulnerabilities. Do they need patching on this one? Looks we're seeing this being talked about, yeah, with patching. Although they do have source now, so it can be source code patching, not binary patching as was the other prior year one. So you're able to use LLMs a lot more because you are dealing with the source code this time around. So it's likely teams will be using LLMs, but it's not necessary. They just want like these artificial intelligence systems that can do the tasks. They're not really specific about how they're doing it. So it's likely they're going to borrow from LLMs, but not necessary.
Yeah. So ultimately, Ben Hawk's opinion here is that it's going to trend more towards augmenting fuzzing, which is kind of like when we've talked about using LLMs and security, that's kind of been our perspective as well, is that it could help a lot with augmenting fuzzing. But when you're talking about static analysis, like pure source code analysis, you kind of run into the same problems that you have with existing SaaS tooling. And that's basically what Ben Hawks points out here. So yeah, I wanted to give it a shout out because it is an enjoyable read. And I think there are some cool insights in here, but unfortunately, there's not much to talk about beyond that, especially because this competition is already kind of underway and it doesn't really seem like something you can get into at this point. So, it's just something we'll have to see what comes out of it, but something to keep an eye on, I think.
He does have some well thought out comments here about just the applicability of AI into some of this, the approaches, all of that. Like it's just generally a good read. We don't have much to really add to that discussion. We've talked about LLMs and fuzzing a few times already. We don't have a lot to add there, but this post I think was still a very good read.
Yeah, and I mean it's Ben Hawks, formerly of P0, like definitely someone has useful insights.
Yeah.
So yeah. The next shout out that we have is a post that's been making the rounds, and it's a Manu Mo post on gaining kernel code execution on an MTE-enabled Pixel 8. So this is another Mali GPU vulnerability and exploit because it goes very specific into Mali, and the it's Mali's kind of unique in some of the bug classes that it has, so it's not very generic. We'd have to get into a lot of the Mali specifics to really explain the bug and how it's being taken advantage of. So that's why we're not doing coverage of it as a full topic. That said, it is a very technical and interesting post. I definitely recommend people to check it out, especially if they're interested in mobile. And it's somewhat notable because, as the title implies, it gets around memory tagging, which is enabled on the Pixel 8. Though, basically, the reason it can do that is because of the unique primitives that you can get inside of Mali. It's just MTE isn't really a factor because you're not doing typical memory corruption that MTE tries to capture. So it's notable. It's definitely worth checking out if you're interested in the lower level like GPU driver style issues, but it sort of falls into the same category as a lot of the Chrome JIT bugs where it's just there's a lot there that you have to get through to really appreciate the vulnerability. And finally, we have another shout out. This is by Satoshi Tanda, and it's a post on SMM isolation, security policy reporting. So that's system management mode. Again, sort of a very specific area that doesn't really transfer well into other research areas. But Satoshi Tanda's posts are they're very good at giving insight into areas that aren't very well documented. So yeah, we still wanted to shout them out here.
Yeah, this is actually part 2 of I don't know how many parts this will have. But it's the second post. I don't think we necessarily saw the first post. I don't think we gave it a shout out at the very least. And yeah, my thing was just this is a deep dive into it. If you're interested in getting into this area, probably worth checking out. Not really any vulnerability stuff in here. It's just getting into the details.
All right. And with that said, that's everything that we have for today. So, as always, thanks goes out to everyone who tuned in. You can find previous episodes on YouTube, Spotify, and Apple Podcast. Also, feel free to join the community by joining our Twitter and Discord. Links are in the description. And if you find some interesting links, feel free to leave them in there because, again, it was a bit of a tough week for topics. So maybe we're missing some stuff. I don't know. But other than that, we'll see you in the next one.